Now that we have a good idea about what free energy is from the POGL, we're going to tie it together with enthalpy and entropy to predict whether or not reactions are spontaneous. So the equation that we're going to use to connect these two is going to be the Gibbs free energy equation, which can be found in your reference table underneath the thermodynamics section. And that equation is listed right here. Delta G, which is Gibbs free energy, is equal to delta H, so our enthalpy change, minus T delta S. And the important thing to remember in this equation is that temperature has to be in Kelvin, and that delta G and delta S have different units. Delta H has kilojoules per mole, delta S has units of joules per mole Kelvin. So before you solve for delta G, which should have units of kilojoules per mole, you need to convert your entropy units into kilojoules, meaning you'll have to multiply your entropy units, divide your entropy units by 1,000. And it's the sign of delta G that's going to tell us whether or not a reaction is spontaneous. The sign of delta G is going to come from the value of delta H compared to the value of the temperature times the entropy change. So in the POGL, you learned that a positive change in the entropy of the whole universe will occur when delta H is negative. And delta H was referred to in the POGL as the entropy of the surroundings. And a negative delta H is an exothermic reaction. Exothermic reactions release heat, and therefore releasing heat into the surroundings will cause an increase in the entropy of the surroundings. Delta S is considered the entropy of the system. And so a positive delta S is leading to an increase in the entropy of the system. If you have a negative delta H and a positive delta S, because temperature is always a positive value, being in Kelvin, you're going to have a negative value minus a positive value. So you can also think of it as a negative value plus a negative value, and that's always going to end up with a negative delta G value. Therefore, when delta G is negative, the process is spontaneous. And the other term for spontaneous is going to be thermodynamically favorable. And that's the one you're probably going to see in many questions pertaining to this on the AP exam. Thermodynamically favorable. So negative delta G means it's a spontaneous reaction. The sign of delta H and delta S will determine whether or not the reaction is spontaneous. So there are two situations where we will always know the sign of delta G. The first is the one we just talked about. If we have an exothermic reaction, meaning we're increasing the entropy of the surroundings, that's a negative delta H. An increase in the entropy of the system, a positive delta S, will always lead to a negative delta G. And I suggest putting these sign values into the reaction and even assigning them numbers so that you can determine the sign of delta G. This occurs at any temperature for the reasons we talked about previously. If you have a negative delta H and you subtract from that a positive delta S, that's always going to give you a negative value. So at any temperature, delta G will be negative. The other situation is the exact opposite of this. If you have an endothermic reaction, so a decrease in the entropy of the surroundings, and you also have a decrease in the entropy of the system, meaning it's becoming more ordered. At any temperature, you're going to end up with a positive delta H. And to think that through, you could assign the values in Gibbs free energy equation a sign, and you could say that a positive delta H minus a negative delta S is the same as taking a positive and adding a positive to it. Well, that's always going to give you a positive delta G. There are also two situations, however, where it's not clear what the sign of delta G will be. The first is if we have a negative delta H, so there's an increase in the entropy of the surroundings, it's an exothermic reaction, which tends to lead to spontaneous reactions, but the system has a decrease in entropy. And this is where the sign of delta G depends on the temperature. So if we put these signs in, so if we have a negative delta a negative delta H and a negative delta S, we have a negative value, and we're subtracting from that another negative value. So you can also think of it as adding a positive. So I'm going to write that in because sometimes it helps to think in those terms. So you have a negative value here plus a positive value because I'm just switching the signs of both. And what you could have is a negative delta G, but the only way you would end up with a negative delta G overall is if the magnitude of the enthalpy is greater than the magnitude of the temperature times the entropy. In other words, this value here for enthalpy, the magnitude, the numerical value, has to be larger than this, so that when you take your T delta S value and you add to the negative delta H value, you need it to stay below 0. You need the delta G value to stay below 0 to be negative. And the only way that can happen is if this value, the T delta S, is a smaller value numerically. So if you want your delta G to be negative, then we need the temperature to be low. Because a low temperature will lead to that situation in which T delta S is going to be a smaller value numerically than the delta H value, and that will lead to a negative delta G. However, at a high temperature, all of which are positive because we're dealing with Kelvin temperature here. At a high temperature, you are going to end up with a T delta S value that is going to be larger in magnitude than your delta H value, pushing your delta G into the positive range. So at a high temperature, you are going to end up with a positive delta G, or a non-spontaneous reaction. And you could even figure out what temperature that would occur at, where it would make the flip from negative delta G to positive delta G, because the numerical value between negative and positive is 0. So if you wanted to determine what temperature would cause the reaction to be spontaneous or non-spontaneous, at what point that would be, you could set your delta G equal to 0 and solve for the temperature. So we could also look at the situation in which we have an endothermic reaction. These types of reactions don't tend to be spontaneous. However, there are some that are. For example, if you take ammonium nitrate or ammonium chloride and you dissolve it in water, the mixture will form, meaning it's a spontaneous reaction that mixture forms. However, the temperature of the surroundings is going to get colder. So it's an endothermic reaction, yet it's still spontaneous. And the reason it's still spontaneous is because the delta S increases. So when you make a mixture, the entropy is increasing. So if you have an endothermic reaction with a positive delta S value, it could lead to a negative delta G still, a spontaneous reaction. So we're going to take a look at how that's possible. So we are going to change our signs here. So instead of a negative delta H, now we're dealing with a positive delta H. And then we are dealing with a positive delta S. So if we're taking a positive and subtracting from it another positive, okay, the situation where we end up with a negative delta G value is when this T delta S value is larger in magnitude than our delta H, because then we're subtracting a larger value, which will push our delta G into the negative. The only way to get this value larger than the delta H is to have a high temperature. So now our high temperature is going to lead to a negative delta G. And if we have a low temperature, that's actually going to end up as a positive delta G, because a low temperature would cause this T delta S value to be smaller in magnitude than the delta H, leaving our delta G as positive. So in the situation that I mentioned before, when you take ammonium chloride and dissolve it in water, even though it's an endothermic reaction, the surroundings get colder, the increase in entropy leads to a negative delta G. So the reaction must happen at a high enough temperature, which ends up being room temperature, that could cause that reaction to be spontaneous. So the way that you're going to see these questions asked is you're probably going to be given a delta H value, a delta S value, and asked about the sign of delta G. If it is either of these two situations, it's pretty cut and dry. If it is either of these situations, you're going to have to think about how the temperature would affect the sign of delta G. So to sum it up, if delta G is negative, the reaction is spontaneous in the forward direction. So I know it's small, so I'm going to write it a little bigger here, but we have a reaction here between nitrogen and hydrogen to make ammonia. And this is a reversible reaction, so it can go in the forward and reverse direction. And as written, if delta G is negative, that means that taking nitrogen and hydrogen to make ammonia is spontaneous. If we skip down to the third one here, if delta G is positive, well, that means the reaction is spontaneous in the reverse direction. So a positive delta G for this reaction as written means it's not spontaneous in the forward direction. Therefore, taking ammonia and breaking it down into nitrogen and hydrogen must be spontaneous. And then this very specific situation exists, and this is going to help you out on some homework questions. If delta G is 0, the system is said to be at equilibrium. So this is that point where it flips from negative to positive or vice versa, whatever temperature that may be. And that is when the system is at equilibrium. And the most common examples you're going to see in this is a phase change. So the temperature at which a substance undergoes a phase change is where the delta G is 0. So something as simple as liquid water turning into solid water. That is only at equilibrium at 0 degrees Celsius. So at 0 degrees Celsius or 273 degrees Kelvin, that delta G value is going to be 0. For the reaction of liquid water turning into gaseous water, that delta G value will only be 0 at the boiling point, 100 degrees Celsius. So when the system is at equilibrium, when it is undergoing the phase change, when it is at its freezing point or its boiling point, that is when the delta G is going to be equal to 0. So Gibbs free energy equation that involves enthalpy and entropy is one way to calculate delta G, and to be honest is the most common way that you're going to see, especially on the AP exam. However, you might have noticed in your reference table that there is a third equation that deals with this products minus reactants idea, just like delta H did, just like delta S did. And that is the delta G form of this equation. It's the same idea. You're going to take the sum of the delta G's for the products, subtract from that the sum of the delta G's of the reactants, and you do get the delta G of the overall reaction. However, because we're talking about standard thermodynamic conditions, this equation is only true if you have temperature of 25 degrees Celsius or 298 Kelvin. And that is the reason we're going to use this more often, because this will allow us to calculate the delta G at any temperature. You'll know you can use this equation if they give you the delta G for every substance in the reaction. I've never seen that on the AP exam. Doesn't mean that it's not possible. This is more likely, however. So here is an example problem in which you're given the delta H and the delta S. I'd like you to pause the video and try this problem in your groups or on your own, and then you can play the video to check your answer. So the first question is asking if the reaction is endo or exothermic, and we look at delta H for that answer. Our delta H is a negative value, therefore it's an exothermic reaction. So we're dealing with an increase in the entropy of the surroundings. The second question is asking us, does the reaction lead to an increase or decrease in the randomness or disorder of the system? In other words, is there an increase or decrease in entropy? And because we have a negative value for entropy, that is going to lead to a decrease in the randomness or disorder of the system. So we have an exothermic reaction, yet there's a decrease in entropy. So we cannot predict whether or not this will be spontaneous until we calculate the value of delta G. So it's going to depend on the temperature. So the third part is asking us to calculate delta G for the reaction at 298. So if we set this up, we are going to plug in our delta H value. And then remember, we need to change our delta S value into kilojoules, so we have to divide that by 1,000. So it ends up being negative 0.0855. And when we solve for delta G, we end up with a value of negative 9.921, and units are kilojoules per mole. And so the question is then asking, is it thermodynamically favorable at 298 under standard conditions? And the answer would be yes, and your reasoning would be that delta G is negative. Another phrase that you may see with thermodynamically favorable is going to be enthalpy-driven or entropy-driven reactions. So a thermodynamically favorable reaction, a negative delta G, can be referred to as enthalpy or entropy driven. And this is going to only apply to those situations where we talked about one of the values, either delta H or delta S, being favorable for a spontaneous condition, while the other one is not. Therefore, it depends on the temperature. And so if a reaction is enthalpy driven, okay, that means that it's exothermic, so a negative delta H, but there's a decrease in entropy. So remember, these are situations in which we've already determined it's thermodynamically favorable. So this is a situation where it's spontaneous, and it must be spontaneous because of its exothermic nature, because its entropy is decreasing. So in fact, this should be a negative delta S here, not a positive. Entropy-driven reactions are going to be the opposite. These are situations where the reaction's endothermic, so it's actually a positive delta H, but there is an increase in the entropy, and the increase in the entropy must overwhelm the endothermic nature of the reaction and lead to a negative delta G overall, so a spontaneous reaction. And so what you see here are those four situations that we talked about before. They're in a slightly different order, but the first and the fourth are those situations in which it's either always spontaneous or never spontaneous. And then the middle two are the ones that are spontaneous at specific temperatures. If you see here, the positive delta S is entropy driven, the negative delta H is enthalpy driven. Here is an example practice problem, okay, that is missing some arrows, but we should have an arrow right here. Okay, and It's a multiple choice that is giving us the delta H of the reaction. So it's asking which of the following is the most likely reason that the reaction occurs at a significant rate only if the temperature of the reaction mixture is greater than 200 degrees. And so I want you to pause it. I want you to look at your possible answers, and I want you to choose one and then play the video and check your answer. All right, so if we're looking at choice A, the reaction is exothermic. That is true. It's a negative delta H. However, that doesn't really give us a reason why it would only be significant rate of reaction if the temperature is greater than 200, because exothermic reactions tend to be spontaneous. So this doesn't lead us to believe that it's temperature dependent. Choice B, delta S for the reaction is negative. Well, that's also true because you have a gas as a reactant and then you have two solids as products. So it's definitely a delta S that is a negative value. However, if we think of our delta G reaction, or a delta G equation rather, and we plug in some signs only, we have a negative delta H and we have a negative delta S. So we've got a negative minus a negative. So we can think of that as a negative plus a positive. And so if we had a higher temperature, like 200 degrees Celsius, that would tend to lead to a positive delta G. Because if this value, if T delta S is a larger value numerically than delta H, then it's going to push the delta G to be a positive value. So that doesn't really explain why it would only occur at a significant rate if the temperature of the mixture is greater. So while both A and B are true, it doesn't support what the problem is telling us occurs. If we skip down to D, D says that delta H is below 0, or delta G is below 0, so a negative value, when the temperature is less than 200. Well, that doesn't make sense at all, because choice D is saying that it's a spontaneous reaction when the temperature is lower than 200, but the question itself is telling us the exact opposite. So that leads us to choice C as our correct answer. The reaction has a high activation energy, and this is what we refer to as a reaction under kinetic control. So if the reaction proceeds or does not proceed spontaneously, and that can't be described using the thermodynamic data like we just showed, then that means the reaction is under kinetic control. That means that the only thing preventing the reaction from happening otherwise, a spontaneous reaction from happening, is the activation energy barrier. And allowing the molecules to have enough energy to overcome that activation energy will cause the reaction to be spontaneous in the end. And lastly, another multiple choice problem here, talking about hydrogen and oxygen being mixed together at 25 degrees Celsius and seeing no reaction occur. When the mixture is sparked, however, the gases react vigorously according to the equation above, releasing heat. Which of the following statements correctly explains why the spark is needed for the reaction to occur when the gases are originally at 25 degrees Celsius? So again, I'd like you to pause the video. I'd like you to discuss these choices and then pick the appropriate answer and then play the video again to check your answer. All right, so if we go through these one by one again, choice A, the reaction is not thermodynamically favorable at 25 degrees Celsius. So the question is showing us that the spark is needed for the reaction to occur at 25. So if the reaction's occurring at 25 degrees Celsius, it's going to be thermodynamically favorable. So that one's out. Choice B, delta H for the reaction has a large positive value. That one is out because it tells us that heat is released, so it's an exothermic reaction. Choice C, delta S for the reaction has a large negative value. Now this one we have to consider because we're going from 3 moles total on the reactant side to 2 moles total on the product side. So is the delta S negative? Yes. However, is it a big enough difference to cause the delta S to be large enough to make it not thermodynamically favorable? Well, we can check that out by looking at the reaction. Okay, and we have a negative delta H because it's an exothermic reaction. And we have a negative delta S. So again, we have a negative plus a positive. And if the reaction had a large positive, if the reaction had a large negative delta S, that would push the delta G to be positive. However, the question is asking which of the following statements correctly explains why the spark is needed for the reaction to occur. If the reaction occurs, it's thermodynamically favorable at 25 degrees Celsius. So the fact that it has a large negative value, the delta S at 25 degrees, would actually cause the delta G to be positive, meaning it's not spontaneous. So that question or that choice does not support what the question is telling us. So that leaves us with choice D. Again, the reaction has a large activation energy. So here's another example where the activation energy of the reaction is going to be the reason why it only occurs with a spark. So this is, again, another one that's said to be under kinetic control. So what you should be able to do through practice problems is predict whether or not a reaction will be spontaneous based on the sign of delta G, and use the sign of delta H and delta S to help you predict that.